All right, guys, welcome back to the last video for kinematics. I do apologize for the delay. Been kind of busy and everything. So hopefully you guys will understand, but I am trying to get these out as quick as I'm able to as well too. So in case you guys are wondering, yeah, I actually haven't recorded this one beforehand. It is actually September 16th when I am recording this motion in 2 and 3 dimensions. But enough about that, right? My hope is to try to, get a few of these out a little bit more frequently, so that way we can kind of have a full set of videos as well. But for today's topic, the last one in kinematics again, we're talking about motion in 2 and 3 dimensions. Good news for us is that College Board actually will not be testing us in 3 dimensions until we get to electricity and magnetism. Even better news for us is that if you're trying to analyze motion or forces or any vector quantity in 3 dimensions, it's actually just an extension of 2 dimensions. And the good news is that 2 dimensions is also an extension of 1 dimension. And essentially, we talked a bit about vectors a few videos ago. We were essentially saying that like a vector can be represented as some quantity I hat plus some quantity times j hat, and that I hat typically represents horizontal, j hat typically represents vertical, and then if you have a third dimension, k hat would be the name of it, and that would be into or out of the screen then. The entire idea, though, behind multiple dimensional motion is that you just have to work with each component individually. So each component of motion does its own thing, essentially, right? We have things like position, which you can see right here. Right, R is typically representing position. And so what this vector is saying is that the total position of an object relative to the origin is given by some number that's classified as x I hat, which means that's x units to the left, or sorry, x units to the right of the origin, right? Remember that x, though, can be a negative number. In that case, it would be to the left. And then y j hat would say that it is y units above the origin. And again, y can also be negative. If we want to actually calculate velocity out of that, the good news is that calculating the velocity vector is just as easy as taking the derivative of each component. And then likewise with acceleration. And this kind of extends from our knowledge in AP Physics 1, where horizontal and vertical quantities, vector quantities at least, were always independent of each other. So there you go, right? dx dt represents the x component of the velocity, dy dt represents the y component. And then likewise for the acceleration, right? That'll be given by the second derivative of position. And this is how you write second derivative, right? For x plus the second derivative of the y coordinate of your position, or equivalently just the derivative of the y component of your velocity with respect to time. Right. And so again, good news with that is that really all we have to do now is just extend things into dimensions, right? But it's important to also understand how to calculate the magnitude and direction of vectors. We did talk a bit about that in our relative motion segment as well. So, we're not really going to spend too much time writing formulas down for that. I want to actually illustrate this with the use of an example. So let's say that you have an object and that object is undergoing motion given by the following. So its x coordinate of position is given by 2 cosine of 3t, and then its y coordinate for its position is given by 2 sine of 3t. And what you can probably convince yourself with this set of parametric equations is that this particle, whatever particle has x and y components of position given by these, is actually going to be tracing out a circle with radius 2. Right? Another way of writing this parametric quantity would be that the position of your object is given by 2 cosine of 3t. So 2 cosine, whoops, my tablet seems to have run out of room to actually write, so I'm trying to realign it here. All right. Okay, that's not really working too well. So I'm going to have to zoom out here. So 2 cosine of 3t I hat plus 2 sine of 3t j hat. So that would be how you could represent this position in terms of our nice I, J, K notation, if you have K, which we don't right now, which is, again, pretty good. Right, if I wanted to calculate the velocity of said object, then all I have to do is take the derivative of each component separately. You can look at your equation sheet. You'll find that the derivative of cos 3t is negative 3 sine of 3t. But then keep in mind that we have that extra 2 out front. So you actually end up with negative 6. You multiply that extra negative 3 that comes out by that 2. So you get negative 6 sine of 3t I hat. That gives you the x component of the velocity, plus, similarly, you're going to end with 6 cosine of 3t for the y component of the velocity. What all of this is saying, though, is if you plug in t is equal to 0, notice that the x component of your position is 2, y component is 0. Right, so that would mean that this object started at the position 2 comma 0, or just 2 meters to the right of the origin. Do the same thing with velocity, and you'll see that the velocity is actually a positive 6 in the j hat direction only, indicating that this particle has a velocity of 6 meters per second upward. The thing that you're always going to notice is that when you actually take the position, it's actually going to trace out a circle of radius 2, and the speed of the object, right? Well, we can actually calculate speed just by taking the magnitude of our velocity vector, right? And if we actually do that, something pretty cool arises. We actually get square root of, and then 6 sine 3t squared is going to give you 36 sine squared of 3t. Sine squared of 3t plus 36 cosine squared of 3t. And we like our trig identities, right? Or maybe we don't, but depending on your taste, right? I actually like this one because sine squared plus cosine squared is equal to 1, and that tells us that our particle, our object, whatever is going in this two-dimensional motion, is always going to have a speed of 6 meters per second, which we know is true in uniform circular motion. So that's kind of cool, right? Again, we know that the radius of the circle that it carves out is 2, because that's where it starts. And both the x and the y components have a 2 with them as well, too. You can check that if you want to, right? But interestingly enough, the speed is also constant. If you do the acceleration, you have to take another derivative, this time the derivative of velocity. So you end up with negative 18 cosine of 3t I hat minus 18 sine of 3t j hat. And so what's happening, you can probably see this, but the magnitude of the acceleration is actually always 18 meters per second squared. And interestingly enough, right, you can actually draw out the acceleration vectors. You're going to see that they're always pointing towards the center of the circle. So this really is describing uniform circular motion for an object, which is kind of cool then as well. Right, but we can even apply things like vectors and two-dimensional motion to projectiles. And that was the biggest application that we had in Physics 1, right, where we have an acceleration value for projectiles, right? So this is for projectiles only, right? But projectiles always had an x component of acceleration that's equal to 0, and a y component acceleration of negative g or negative 10, right? Remember that g itself is inherently positive, so you have to say negative g to indicate a downward acceleration. Another way of writing this in our lovely I hat j hat notation is just negative g j hat, right? Magnitude of negative g in the j hat direction downwards, right? Or negative g, magnitude is 10, right? G, and then downwards rather. So take a look at this problem. A soccer player is trying to score a goal from 10 meters away. The goal is 3 meters tall. They kick the ball at that speed and angle. Will the ball make it into the goal, right? Another way of actually reading this question is, if the ball goes 10 meters horizontally, will its height be less than 3 meters, right? Because if it's not, then that means either the ball overshot the goal, or if the height is less than 0, once it goes 10 meters horizontally. It didn't even make it that far. So, right, so essentially we have this ball goes at an angle of 30 degrees. We're trying to check to see, does it end below that 3 meter line that I just drew or not. The way that we can figure this out is we have to use our kinematics equations. This is uniform acceleration, right? So we do have to use our kinematics equations. I actually kind of like creating a chart for projectiles because there's a lot of stuff going on here. And it's nice to keep all of that stuff pretty pretty organized. So we've got two different columns, one for horizontal, which I'm going to call H, one for vertical, which I'm going to call V. And a couple of things that we know here is we know that we want the ball to go 10 meters horizontally, right? That's kind of our starting point. And again, we want to check to see what the height of this ball is going to be and compare it to that 3 meters tall. So we know that. We know that the initial velocity is going to be given by 20 cosine of 30 for the horizontal. And it's going to be 20 sine 30, which gives you 10 for the vertical, right? The final velocity is the same for the horizontal as the initial. We do not know the final vertical velocity. We don't know how much time this thing is going, but we do know both of the accelerations, 0 and -10, all in their respective units for position, velocity, acceleration, right? So the first thing that we want to do is we're looking for height. Look at our vertical column. Do we have enough quantities to use any kinematics equation with just vertical values? The answer to that is no, right? We need three kinematics quantities to find a fourth unknown if we're using a kinematics equation. So the first thing that we want to do then we want to find one more quantity for our vertical. And the quantity that we can use is time, because time is the same between both horizontal and vertical since it is a scalar quantity. So let's go ahead and find time using just horizontal values. That one's actually pretty easy because we don't really care about the final velocity here. So you can say that delta x is equal to v naught t plus 1/2 at squared. But our horizontal a is 0. So therefore, what you get is that 20 cosine of 30, which if my memory is not failing me, it would be about 17.3-ish, right? For our displacement, not for our displacement, sorry, for our velocity, right? 10 for our displacement, about 17.3 for our initial horizontal velocity. So 10 is equal to 17.3 times t then. So if we want to actually solve for time, well, that's not too bad then. We can just go ahead and plug that into our calculator. You get 10 divided by 17.3. That tells you that the ball is going to be moving for 0.578 seconds in order to move 10 meters horizontally. Right, now that we know that, we can find how far vertically the displacement is going to be in that amount of time, and then again compare that to 3, right? So delta y is going to equal the initial velocity times time, right? So 10 times 0.578, and I just kind of realized, don't be like me actually. Write your equation out before you substitute in values because it's good to get in that practice. I apologize. Let me go ahead and do that right now. It is the same equation that we used for the first part. So hopefully you can forgive me for that. But in any case, right, still good to do it. So minus 5 times 0.578 squared. Right, so if you go ahead and you compute that, then this looks like a lovely number. Let me go ahead and do that real quick. I have my calculator off screen. So that's going to give us, let's see, 5.78 minus 1.67. That's going to give us a height of, or a vertical displacement of 4.11 meters. So in other words, when the ball is at a horizontal position of 10 meters, the height from the ground is 4.11. It's a positive number, which means thankfully the ball is still in the air. But unfortunately, since it ends at a height greater than 3, that means that it did not make it into the goal. It's actually going to overshoot it. So it's actually ending a meter, 1.11 meters above the top of that goal, unfortunately. So the ball will not make it into the goal. Right, so that's kind of a cool little thing that we can do with projectiles. Another thing you can do is you can work with symbolic expressions as well. And so, in terms of that, right, we have that a projectile is launched horizontally from some height and speed. In terms of height, speed, and physical constants, which is g essentially for right now, derive an expression for the range of the projectile. Right, so we can actually use kinematics equations for this. Symbolic derivations are very, very common on RAP exams, right? So we have a couple of things that we're going to want to do, right? We want to figure out how to get range. We want to figure out how to get horizontal displacement, right? Well, the good news is that we know quite a few things here, and we want to approach these. We want to approach these symbolic questions much like we approach regular questions with numbers, right? Plug in, figure out what you know, figure out what you don't know, figure out what you don't care about, figure out which equation to use, right? We are looking for horizontal displacement. I'm going to put a question mark there. We know that the vertical displacement would be negative h. It goes down a height h before reaching the ground. The initial velocities are v and 0 because it's launched horizontally. Final velocities, right, those are going to be v and an unknown number, and then accelerations are 0 and negative g. Although it looks like we could just find range using horizontal quantities, note that the initial and the final velocities are the same, so we actually will not have enough information, unfortunately. That means we have to figure out a symbolic expression for time using our vertical values. We don't care about final velocity, so I can say that delta y is equal to 1 half at squared. Note that the initial vertical velocity is 0. Right, so if I solve that for time, then plug in negative h for delta y, plug in negative g for a, you're going to get that the amount of time it takes this object to hit the ground is going to be given by square root of 2h over g then, which makes sense. The higher you launch a projectile, the more time it takes to reach the ground. The stronger gravity is, the less time it takes to reach the ground. Right, and then we can do the same thing for delta x using the same equation, but with a non-zero initial velocity and a 0 acceleration. So that's going to then tell us that delta x, which is the range, right, that's r, if you want to call it that, is given by v square root of 2h over g. And look at that. We now have a symbolic expression in terms of h, g, and h physical constants in v. Right, way of reading this expression, of course, is the higher up an object is launched from, the farther it'll go horizontally, right? The more speed you give it, the farther it'll go horizontally, which hopefully makes sense because you're launching it horizontally to begin with, right? Now, interestingly enough, you notice that if you actually quadruple the launch height and keep everything else constant, you're actually only going to increase the range by a factor of root 4, which is going to be 2. So quadruple the height, you're actually only doubling the range, which is kind of an interesting thing, right? You might not have expected that. And so actually using these mathematical expressions is very, very helpful for being able to understand the trend between two different things. Right. As a matter of fact, if I were to now take data for a projectile that's launched horizontally, and let's say I wanted to plot a linearized graph for range and height, what I could plot is range and square root of height, and that would actually give me a straight line with a slope of v times square root of 2 over g. And you can get that because you have your symbolic expression. You just divide by root height on both sides. That'll give you rise over run for this graph, which we know is going to be constant. Speed is a constant, and then 2 is a constant, and g is a constant as well. So essentially, we move all of the things that we would be changing in an experiment over to one side of the equation, leave the constants on the other side, and that'll allow you to create a linearized graph with some constant slope then as well. All right, so that does it for kinematics then. That's about all I want to go through for this. You know, there's plenty of other examples that we could do overall too. I'm sure that your teacher is going to be providing you quite a few of those too. But yeah, hopefully you guys found this helpful. Next video, we will start off with forces. And so hopefully you guys are excited for that. So thanks for watching, guys. I'll see you in the next video.